Hi, this is Hassan Adib. Today I'll present the outcome of our empirical study on the impacts of AutoSklearn learning settings. These learning settings are meta-learning, ensembling, time, budget, and search space size. I will start by identifying what automated machine learning is, and as you know, the machine learning experts are working to produce a pipeline that maps the input features into the target output, and automated machine learning frameworks are working to do the same task, producing this pipeline by optimizing the following objective function. The main part of this objective function is to find the pipeline that minimizes a particular selected loss function. AutoSklearn is using Bayesian optimization to solve the previous objective function and find the best pipeline. This is the good news, which is the pipeline will be produced automatically, but the user has to select and identify some learning settings. We will start by the meta-learning. The user has to select whether to include or not to include meta-learning, and meta-learning offers some pipeline configurations to overcome the problem of cold start of the Bayesian optimization technique. So the Bayesian optimization technique will start from these recommended pipelines instead of starting from random configurations. The user also has the choice to select or to have the to make the AutoSklearn report an ensemble model instead of just reporting the best performing pipeline. The user also has to select the time budget or the time allowed for the AutoSklearn to search for the best performing pipeline, and to identify the search space in which this AutoSklearn will traverse to searching for the best performing pipeline. We set our experiment to answer the question of when and how to identify these learning settings, and we use 100 dataset from AutoML that covers several meta features of these datasets. On each run, the AutoSklearn has been run over 4 different time budgets, and we used 4 different configurations of AutoSklearn vanilla that includes only the Bayesian optimization technique, and /m, which includes meta-learning, /e, which include ensembling, and the full version that includes meta-learning and ensembling we annotated using just AutoSklearn. We also compare the performance of the best performing classifier. We select the 3 best performing classifiers and compare their performance into the full search space. We found that this is for example for meta-learning, there is no configuration that produce a performance gain for all datasets. Some datasets are working well without meta-learning, and some others are working well with meta-learning. But when we run the Wilcoxon test to compare between AutoSklearn M and AutoSklearn V, we found that AutoSklearn M is doing well with them and adding a significant performance gain with small time budgets. Ensembling also doesn't guarantee a significant performance gain for all data sets, as we see here, but on average, when after running the Wilcoxon test, we found that on average it adds a significant improvement on the performance for all the selected time budgets, the 4 time budgets. Increasing also the time budgets sometimes improve the performance, and sometimes it doesn't. As we see here, after running the Wilcoxon test, increasing the time budget from 60 minutes to 240 minutes doesn't add any significant improvement over all the 4 configurations. Also using a subset of the classifiers or a small search space almost produce the same results, and that's extremely useful for large data sets that where the optimization techniques cannot run many cannot evaluate many pipelines. To conclude, we have introduced this experiment to answer the question when and how to identify and or define the learning settings of AutoSklearn. And this study actually opens the door to adaptively configure the search to configure these learning settings for each input dataset. That's all from our side. Thank you for your attention.